I'll just pick it up right after here. I mentioned the features of different arteries, and I want to look at some histology pictures now. So let's look at the next slide. Turn off the light so you can see the image a little better. This is cardiac muscle. I start with the heart because the heart pumps blood into the vessels. They're continuous here. Be able to identify this slide or a slide like it, like when I take a picture. It's cardiac muscle, things to notice, the striations. And notice how the dark bars, the intercalated discs, are kind of in the same orientation as the striations. You see a lot of nuclei. You see that it's highly branched, it's cardiac muscle, and be able to identify the intercalated discs. That's the cardiac muscle, which pumps blood into the arteries closest to the heart, which are the elastic arteries. So this is the vessel wall of the elastic artery. And to orient you, I indicate the tunics. The TI, tunica intima, TM, tunica media, and TA, tunica adventitia. So from top to bottom. Look how big the vessel wall is. So that's the lumen. And so you got 3 layers. Be able to identify the tunics, know that this is an elastic artery, the artery is closest to the heart. Be able to identify the tissue/cell types we talked about. I said that the TI is an endothelium. I said that in the TM, there's a combination of, well, what you'll see color-wise is black and pink, okay? Pink, smooth muscle cells. The black, elastic fibers, okay? So in the TA, it's mostly collagen fibers. And what you can notice is, there are tiny blood vessels in the TA. And I kind of like blow them up here. I might have you identify that within the TA. It's the vasovasorum. Let me say it there. The vasovasorum of the TA. So that's an elastic artery, the ones closest to the heart. As arteries branch out and branch out and branch out, they become smaller. Like this one. This is a muscular artery. You can see the whole vessel here. There's the lumen. And the 3 arrows point to the 3 tunics. The TI, the TM, and the TA. And now we must write it out on, say for example, an histology quiz. Tunica intima, tunica media, tunica adventitia. And what I see here, this black, dark structure, looks like it's kind of like elastic, is the internal elastic lamina. On the TM, what I see is that it's more pink than black compared to the previous slide. It's more black than pink. Here, more pink than black means more smooth muscle. That's why they're the muscular artery. And this is all tunica adventitia. Here's another example. This is from the rat testes slide. And as an instructor, I just got to know where to look for them because I know that testosterone has to get in the blood vessels, so I just look for blood vessels on the rat testes, and here's one. And again, the 3 arrows point to the 3 tunics. Say, for example, what's this middle arrow pointing to? TM, TI, TA, and those black cells aren't red blood cells because it's a blood vessel. It's a muscular artery. You got all 3 layers. Okay? When you get down to 2 layers, you may have to identify this as an arteriole. There's TM, TI, no TA. For the 2-layered arteriole, they're the smallest blood vessels. Now this comes from spleen. You haven't had that yet, but interestingly enough, you know, white blood cells of the spleen stain purple. Okay. So that's why they call it white pulp, because it would be white on a fresh dissection. And white blood cells in the spleen helps fight against blood-borne infections because you have these cuffs of white blood cells that surround the blood coming in. So if there's a blood-borne infection, the white blood cells can fight it for you. All right. But anyways, for this lecture, you have to identify that as an arteriole with 2 layers. Here's a closer-up picture of an arteriole. with two layers, just TI and TM. Okay? By definition, one or two layers of smooth muscle cells kind of makes it an arteriole. Okay? In all, you have two layers, TI and TM. That's an arteriole. It's from the spleen. It's our example of an arteriole in this lecture. When you get down to one layer, you're talking about capillaries. I haven't described those yet, so let me turn the lights back on. Well, let me get my bullet points up here. First, if you look at the histogram, that's all they are. They're just an endothelium, one layer. Okay? This makes it good for diffusion. You have to diffuse, for example, the blood gases across it, nutrients across it. And so it's just one cell layer thick with a basement membrane, of course. They're very short and their diameter is very small. That's only big enough to allow the width of one cell to get through. So cells have to line up single file to get through that diameter. That's how small they are. But they're very dense. Even though they're very small, there's a lot of them. And we kind of talk about the area for blood to flow in terms of centimeters square. Okay, so you'll see that a lot. Cross-sectional area. All right, turn the lights on here. And another phenomenon called rouleau. So capillaries. They're just a TI, tunica intima, an endothelium with a basement membrane. They exist in beds, which provide lots of cm square, cross-sectional area. Physiologists like to use that term a lot, cross-sectional area. I mean, we never really calculate it. We just say there's lots of room for blood to flow. That's what you should say to yourself conceptually in your mind when you see that. You ever been like, say, whitewater rafting? You're in the rapids and the boat's going fast and you try not to fall out of the canoe or whatever, you got your life jacket on. And then you get to the end, and you get to the wide expanse. What happens to the flow of water in your boat? Does it speed up or slow down? It slows down. Now why? Because that finite amount of water, which was trapped in the narrow whitewater rapids, now has this wide expanse as an outlet. The rules of physics say velocity is going to slow down. The same is true for blood. The velocity of blood flow slows down. Now, I know you haven't taken physics, but like when you drive your car miles per hour, velocity is a certain speed per unit time. Say blood flow is slowing down centimeters per second. That's good. We'll allow time for exchange. That's what I'm writing here. Allow time for exchanges to occur. Now that exchange requires lots of explanation, so we'll come back to that. But the last term I have, I think that's the last term, let me see. Yeah, rouleau. I believe that's French, if I'm not mistaken. Anyways, that term means the blood cells have to line up single file. They kind of stack. They have a tendency to stack and file through capillaries. So what I'm writing is the RBCs stack and flow through capillaries single file. So here's a picture of that. You have muscle fibers, capillaries within the muscle fibers, and then singular rows of RBC stacking up and filing through. Now, so there's varying degrees of leakiness for capillaries depending on the location of the body and its function to allow more efficient exchange depending on what you have to exchange. So, you have capillaries that are continuous. You have capillaries that are called fenestrated capillaries. You have capillaries that are called sinusoidal capillaries. You know, to summarize, I simply put, well, the continuous capillaries are called continuous because the endothelial cells create a continuous layer. Okay, there's not a lot of space between them. So continuous layer formed by endothelial cells, which I frequently abbreviate ECs. So these allow exchange, but not very much. They're not so leaky. Okay? And locations where you want exchange to take place, but not too much, is places like, say, skin, where skin is a barrier to infection. It's your first membrane defense against acquiring infection. So you want these kinds of capillaries to be in skin, so help keep infection out. Skeletal muscle. When you work out, there's a buildup of lactic acid, and you want to kind of keep that acidity out of the blood capillaries. So those are a couple of places where you have continuous ECs, not so leaky. Fenestrated capillaries are more leaky. So what we mean by that is there's gaps and fenestrations. A fenestration is a tiny hole in a cell. So the tiny holes or fenestrations in the ECs, but there are also gaps between the ECs, larger gaps than in these ones over here. And so this allows exchange of larger molecules. For example, you might see these in the capillaries in the glomerulus in the kidney. The kidney has to filter all the blood plasma, so those are highly fenestrated. Also in the smooth muscle, intestinal capillaries. Not smooth muscle, small intestine. Small intestines. Because they have to absorb all the food nutrition, like, you know, carbs and proteins. And so you want larger spaces so those molecules can pass into the intestinal capillaries. Well, I guess the leakiest capillaries, which have very large gaps, fenestrations, are the sinusoidals. They're so large that you have to allow whole cells to enter the bloodstream. You have sinusoidal capillaries in, most notably, the bone marrow. The red marrow produces the blood cells for an adult. So bone marrow is a good example where you find sinusoidal capillaries. I have one close-up picture of an illustration of a capillary with its basement membrane. Here's the cell. You can see there's little holes in it, the fenestrations, and there's gaps between the ECs. So fenestrations and pores called fenestrations or pores. Here's a slide of a real fenestrated capillary. It's the example from the kidney, the glomerulus. Don't look at the black arrows. I mean, look at, if you see one little crater, it's like, it's completely covered with tiny holes, okay? Those are the fenestrations. This is the inside of a capillary. So this very efficiently filters blood plasma for us. So if you have a toxin in your blood, the kidneys can filter it out, okay? Okay, next picture is an image. Let me turn the lights back off. So again, when I'm looking for capillaries, I mean, the slides aren't labeled, but teachers or students, if you just know what to look for, you can identify it. I'm looking for how many layers?
One.
For a capillary?
One.
Just one, just the TI. And I said that they're wide enough to allow one cell through at a time. So when I saw this, that's about one cell. That looks like one layer to me. I just call it a capillary. Okay, just know the rules and you can do it yourself. So capillaries, you get capillary exchange and more on that in a minute, but what collects the blood from capillary beds? Veins. So let's talk about the characteristics of veins shown here. We got the one layer, the venules basically start collecting them. Back to 2 layers. So I'll put a 2 for 2 layers. What you see there is a TM, TI, no TA. So that having been said, identify that cell. I'm pointing to the outermost layer. What's a cell in the outermost layer? You should be able to identify that. Smooth muscle cell. All the blue cells are like of the endothelium. That's what you see there. The function is to collect the spent blood from capillaries. They collect that blood and they kind of send it to veins, large veins, small veins. Well, anyways, the vein they show there you're back to 3 layers. They're all there. And if you look at the histogram, veins, compared to arteries, they have a significant TA. They have a lot of collagenous material. You have all 3 layers, prominent TA. Okay, the largest veins have very large lumens. That's the key property there. We have some pictures of venules and veins. Now in the liver, you have a venule. You can barely see the two layers, but I just kind of know it by definition. It's in the liver, it's a venule. And what you got to do to identify it is the liver tissue is arranged into lobules. And if you look at the center of it, that's going to be your venule. Okay, so remember that liver is the example of venule. Muscular artery, large vein, unlabeled. Could you tell the difference? There are clues. If I see a very pink TM, I know it's an artery. Usually the vein is larger, but not always. You just kind of have to study the images that are provided to you. Here's a close-up picture of the large vein. And there's 3 layers here. If I point to this one, here's the lumen. So if I point to that one, just by geography, where is it? By location. TI. It's kind of pink here. What's this one? TN. And color changes here because that's collagen and elastic tissue. What is this? STA. Here's a close-up picture of that one, and they're all labeled. Well, they're bracketed but unlabeled. So TI, TM, TN. Okay. All right. So to circle back to capillary exchange, let's talk about this now. Here's some terms I have to define. These terms I'll just kind of talk over. You know that plasma is the liquid part of blood inside capillaries. There's all the fluid outside cells and outside capillaries. That's a fluid compartment, the interstitial fluid. Sometimes we call it the extracellular fluid. And all the fluid inside cells is the intracellular fluid. There's 2 different kinds of pressures that I should define. Hydrostatic pressure. So when blood flows from the heart to the arteries, to the smaller arteries, to the smallest arteries called arterioles, finally gets to the capillary beds. Hydrostatic pressure is a pressure that actually it pushes fluids out of the capillary. We call that filtration. And this pressure changes from one end of a capillary to another. It drops as it flows across a capillary. Maybe at one end of a capillary, pressure's higher. 32 millimeters of mercury. By the time you get to the end of the capillary, because you've pushed fluids out, the pressure drops to something like 15. Something like that. There's a range. You know, there's a pressure that opposes this hydrostatic pressure. It's the colloid osmotic pressure. Now, colloid osmotic pressure basically draws fluid into a capillary. It's a force. Causes absorption. Like think about the rules of osmosis. Water usually flows to where the most stuff is, right? But the concentration's higher. That's why the word osmotic is in there. So things like salt, albumin, your crit, your red blood cells, all the stuff that's in blood helps contribute to this pressure. It draws fluids into the capillary, it keeps fluids into the capillary. Okay? So one forces fluids out, one forces fluids in. So these two are always opposed to each other. If hydrostatic pressure is greater, you have a net filtration. If osmotic pressure is greater, more fluids enter. So the pressure usually stays pretty constant, and it stays right around 25 millimeters of mercury. Now remember, this 25, it opposes this pressure. Okay, so sometimes people put a negative sign in front of it because the force is in the opposite direction as this pressure. Okay. The other thing, besides exchange of fluids, you have exchange of everything else. Blood gases and nutrients, they exchange on the principle of diffusion. You flow down your gradient from high to low. So what I'm writing is blood gases and nutrients exchange based upon their concentration gradients. Now, some see these principles at play. Just kind of look at this figure here. This is a common model of capillary exchange. Instead of showing a whole capillary bed, they just show a single capillary to simplify it for students. And you see all the fluids coming in. 7,200 liters daily comes in, goes out, a single capillary. You have an artery side and then the vein side. And they show it turning from red to blue, symbolizing gas exchange. So it's good to think about capillary exchange in terms of 3 locations along any given capillary. In arterial end, blood's coming in. The red end, basically, some midpoint, some midsection, or close to it. And then some venous end. Okay, well look at this end. Now, okay, it's hard to see there, but let me point to what I'm talking about. Where they say P cap, that's hydrostatic pressure. Where they have the symbol pi, that's the osmotic pressure. And they have 32 minus 25. And the P cap, that's the filtration pressure. It's like pushing the fluid out. But the red arrow is the pi cap, negative 25, and it's sucking fluids in. Okay. But because 32 is greater than 25, there's net filtration. So that's what you got to know at the arterial end. So P cap is 32. It's greater than the osmotic pressure, the colloid osmotic pressure, which is is negative 25. So the filtration pressure is greater than the colloid osmotic pressure, therefore you have net filtration. And filtration always refers to the fluids being pushed out. But you also have oxygen diffusing out and nutrients diffusing out at the capillary end. O2, nutrients diffuse out. Then at this point here, at some point as fluids get pushed out, you have less net flow out. And the point at which these forces are equal, the hydrostatic, the P cap, is equal to the pi cap. They're both like 25 in the opposite direction, so they just kind of cancel each other out. Yet you have no net filtration or absorption. Let's just call it no net fluid flow. And there's nothing else, there's no net diffusion of anything either. I just want to put it, nothing's happening at this midsection. When you get to the venous end, P cap is 15. And pi cap is still negative 25, doesn't change. And you have a greater force in, so there's net absorption. And this is the side of the capillary where CO2 and cell waste diffuse in. Diffuse into the capillary. So that's what I wanted you to see there. Just pay attention to which force is greater. Pay attention to diffusion. And the picture in the Marriot textbook is a little different, but I included it here just to summarize. Good figure. They have fluid exchange, the filtration, net filtration at the arteriole end, no net fluid exchange, and then they have the arrows pointing inwards, symbolize the absorption or reabsorption at the venous end. Then they have the same thing for the metabolites. Well, there's net O2 and nutrients diffuse out, and then net in CO2 and waste to get into the venous blood there. Also, to remind you, the other thing I mentioned was as you branch, you have one tube that branches into many smaller tubes. The net result is, with all those branchings, even though you have smaller tubes, you have many more of them. So you have a net increase in total cross-sectional area. And if you were to monitor the velocity of blood flowing, as cross-sectional area increases, the velocity of blood flow, especially at the capillaries, slows down. You kind of wrote that down before. It's a concept I want you to remember. Capillary exchange. As you increase cross-sectional area, you decrease the velocity. So I'll just give you the units. Increase cm squared, decrease centimeters per second. Okay. That's what I want you to see with that data. Capillary exchange out of the way. I want to talk more about the physiology of blood pressure. Talking about blood flow, blood pressure, and resistance to blood flow. These are, I'm basically boiling down the chapter to 3 bullet points, and there's a lot to unpack there. Because it's very important for students to understand how mean arterial pressure is maintained. Okay. And they use the same terms as the cardiac cycle, inflow and outflow. But this time, the structure is systemic arteries, not the ventricles. I have a picture and a couple of concepts there. We'll just look at the picture and be very simple. What side is bigger, the red side or the blue side? In terms of the blue side's bigger. Those are the veins, and those are the capacitance vessels. And look at those little equations in there. Like, oh no, an equation. We already talked about it. You're like, no, we didn't. It's like, yes, we did. We talked about it. CVP. Go back and look at your notes. C is capacitance, volume, and pressure. The whole thing where I talked about capacitance is a function of, pressure is a function of volume capacitance. So, I mean, here, let me remind you of that conversation. Did I say, take the red side first, the arteries. Do arteries hold a lot of blood or a little blood? A little blood, 15%. Okay? So imagine in the numerator, volume of blood, a small number. Do we observe high or low pressures in the arteries? High. So if you have a small number divided by a large number, that gives you a small number. The capacitance of arteries is fixed, it's small. They don't hold very much. Okay. Now let's remember our conversation about veins. Do veins hold a lot of blood or a little blood? They hold a lot. The volume is large, so a large number in the numerator, but what about the pressures, high or low? Low. When you divide a large number by a small number, you get a large number. The capacitance is very high. So we did talk about CVP already. What else is up there? For large arteries, the capacitance is small and it's fixed. Therefore, arterial pressure is controlled mostly by controlling the inflow and outflow into the arteries. So this time, when we talk about inflow into the arteries, how does blood get into the arteries? The heart pumps it into the systemic arteries. Which chamber of the heart is it? You just took a test on the heart. The LV. We're talking about systemic arteries, so it's LV. What's the valve that you got to get past to get into the artery? The aortic semilunar valve. Yeah, so all that stuff is coming into play here. So the inflow is controlled by cardiac output. Right? So the outflow is controlled by the resistance here at the artery. What's the smallest artery called? Arteriole. So they kind of control most of this outflow. Right? So inflow and outflow. So the thing to know about the human body in regulating blood pressure, the body can sense blood pressure but not blood flow. This is what the body senses, the pressure, not the flow. That's okay, because if the pressure is high enough, blood will flow. That's all you need to know about that. So this is why blood pressure is a vital sign, not blood flow. Okay. Blood pressure, something about that. So pretend you're a nurse or clinician, and your job is to monitor your patients. You got to take their vital signs, or maybe a machine does it for you, but you got to look at the data, right? At the time BP is measured, it is an indication of blood volume at that given time. there's different ways of saying that. Because arteries, they don't hold a lot of blood. So it's completely determined on this inflow and outflow of blood in the arteries. It doesn't change very much. So when you measure the blood pressure, that's how much blood is in the arteries at any given time. What if the blood pressure is dropping? They're probably losing blood or something's wrong. I mean, you know, if someone's in the ICU, you probably have to take blood pressure readings every 30 minutes to make sure they're okay. You closely monitor that. So let's talk about blood flowing. Blood flowing is not what the body senses, but we still talk about it. Blood has to flow. And in the physics class, when you learn how fluids flow of a liquid is determined by symbol F. You study Poiseuille's law in physics class. Well, we don't necessarily do that. For our class, blood flow is determined by cardiac output. So I'll just use that for flow. Blood flow is determined by cardiac output, CO. And since we know what that cardiac output is a product of heart rate times stroke volume, I'll just put that too, because that's really what's going on there. The heart's beating, and with each beat, there's volume injected. So that determines blood flow. And flow, you've got to have some parameters here. It's flow of a liquid past a fixed structure per unit time. Flow past a fixed structure per unit time. So for us, let's let that fixed structure be the aortic valve. That's the cardiac output. That's the blood flow for us. So you get enough cardiac output, then the blood pressure should be high enough. And let's talk about the blood pressure that we measure in people. The enclosed blood exerts a force or pressure on the vessel wall. So there's kind of a picture of that. It's kind of a free body diagram. They show you a portion of a vessel in the leg. And you kind of going out here, and you have, well, actually there's three kinds of pressures that we define here. So when we talk about blood pressure, you know, it's always a pressure difference between two locations. That's the key. Pressure difference between two locations. That's what the figure is showing you. Hydrostatic pressure is one example. We consider that because this is the pressure against gravity. We're bipeds, we're not quadrupeds. I mean, just like even sitting there or standing up, the heart has to pump blood from your chest up to your head, okay? You have to fight gravity. And in this example here, it's the delta H, H1, H2 in the vertical axis, right? So figure it's delta H. Delta is the symbol for change between two locations, the H1 and H2 on the figure. Okay, let's look at this one here. If you look at here, they kind of like take a piece of the wall and they zoom it up. And you have the inside of the wall and you have the outside. You have inside and outside of the vessel. This is called the transmural pressure. The mural is a wall. Transmural means the pressure difference across the vessel wall. I'm going to start next to this one. This is the pressure that your body can detect. It's the pressure difference across the vessel wall. I'll just be specific. What do I mean when I say the body? There's a cranial nerve 9. Talk more about it in another lecture. For now, just look that up if you need to. It's called the glossopharyngeal nerve. Okay, so it's detected. Pressure across. The vessel wall. R1, R2, it's the delta R, I guess. The reason why you can detect this one is nerve fibers exist inside the vessel wall. And so if the wall stretches out, pressure is increasing. And the nerve can pick up on that, okay? Because it lives in the vessel wall. So that's why it's the one you can detect. So it's good to have those sensors. I mean, not every blood vessel has it. There's two locations, the carotid and then the aortic arch. Those are two places. And they're close to the heart too, right? So that's good checkpoints. So a place called the carotid sinus and the aortic arch. All right, the third pressure, the delta X inside there, this is the important one. This is the pressure difference along the axis of the blood vessel, okay? Let's call this the driving pressure. I guess I had you put a star next to the transmural pressure because it's the one your body can detect. Maybe you should double star this one. This is the pressure that causes blood to flow. It's the pressure along the central axis of a blood vessel. So for example, because it's a pressure difference between two locations, what determines this driving pressure is a pressure gradient, not absolute blood pressure. So what I'm writing is pressure gradient determines the blood flow. Not the absolute pressure. In other words, it doesn't matter how high the pressure is. What matters is how steep the pressure gradient is. So to illustrate that idea, look at A and B, and let's answer the question. Well, which one's going to have a greater flow rate? Vessel A vessel B, or is flow equal? Okay, it's got to be one of those three choices. And I give you the numbers, 90, 10, 175. How do you figure out a gradient? Don't you subtract? Yeah. What's the gradient for A? There's a difference of 80. There's a difference here. 25. So what will have a greater flow rate? All of the things being equal. A will. The steeper gradient does. Okay, students might look at this and, you know, I get this question asked a lot, which is why I have this. Well, 100's higher, so it's going to flow more. Well, not if the thing you're flowing to is very high too. It's all about the gradient, not the absolute number, right? Okay, so then you just bring it back to the cardiac cycle. What cardiovascular structure generates this blood pressure gradient? Well, it's got to be the left ventricle. That 120 millimeters of mercury pressure, that's it. That's the structure. Okay. Because we can't look at this tube in a vacuum. What's creating the high end? You know, when you measure someone's blood pressure, are you measuring both ends of the tube? Yes or no? No. Think about what the heart is pumping blood to. The arteries. And what's the artery's job? To get blood to the capillaries. Okay? So think about that. The goal is the heart. You pump it to the arteries. You get it in the capillaries. But when you measure blood pressure, where do you put the cuff? On the arm. Now what's the artery in there? The brachial artery. We'll learn that. So you're only measuring the blood pressure from the brachial artery as an example. You put it around your neck, I guess. That wouldn't be very comfortable. But the point is, when you take someone's blood pressure and it's 120/80, you're measuring this end of the tube. And if it's high enough, what you say to yourself as a clinician, oh, there's enough pressure to push the blood to what? The capillaries for the gas exchange, and bloods don't, you know, tissues don't die. So what if the high end, what if this number drops? 90, 80, 70, 60. I mean, people know that this is bad, right? If there's no gradient for blood to flow, then blood will stop being pushed to the capillaries, and that's when shock can occur. So, you know, that's why we measure blood pressure. So if you didn't realize that, realize it now. That's very important. But you're measuring the high end, enough pressure to push blood. Okay, peripheral resistance. So we talked about the inflow. We talked about how you measure blood pressure. And now let's talk about what's called the outflow. Okay, you have to control that. If you dilate that and all the blood leaves the arteries, that can lead to shock too. Because if all the blood leaves the arteries, where does it go? To here. It could just stay there. These are your capacitance vessels. All the blood stays in veins away from everything else, and that could cause shock too. So we have to control the outflow. Peripheral resistance. Resistance is resistance to blood flow. Okay. Usually symbolized by capital R, resistance. And, well, 4 determinants there. Now, most of these are constant, so let me kind of go through them. Blood viscosity. Think about things that causes blood to flow, resists blood to flow, and we've got viscosity. In adults, it stays pretty much constant. It's just the physical goopiness of your blood. Like, for example, syrup is more viscous than water, right? The thickness of it. And it's largely determined by your hematocrit, and in adults, that usually doesn't change. So it's pretty constant. So I don't talk about it too much. But the rule is, if you increase viscosity, you increase this. If you were to do it, you would increase capital R. Okay. All right, blood vessel length. Okay, if you increase the length of a blood vessel, because the main source of resistance is friction against the vessel wall, is the main source. Simply because you have, again, all other things being equal, assume those are equal, we'll try and draw them equal. A longer blood vessel has more resistance simply because it's longer. So there's more friction only because it's longer. Now that doesn't usually change either, because in an adult, you stop growing, your blood vessels stop lengthening. Maybe if you put on like a lot of weight, all the extra tissue needs more blood vessels, maybe that would increase the resistance, but we won't consider that. Just assume it stays pretty constant in adults.
What about when you're pregnant? Does that?
Yeah.
That is too?
Yeah, in fact, that increases the blood volume too. But it also, you can't keep all that fluid in the vessels, and you have a lot of edema too. Yeah, that would be true. Okay, turbulent blood flow. Turbulence. Okay, turbulence can be caused, turbulence as opposed to laminar. Laminar would be the opposite word for that. Laminar, think of like nice, smooth, straight lines, symbolizing straight, smooth, non-turbulent flow. This will be laminar. Okay, pretend this is inside a blood vessel. Blood is flowing. But let's say you have a plaque in the vessel wall, like from atherosclerosis. You have a little bump in the road. When the smooth blood flow gets to the bump, it causes turbulence. Or if you have a branch, arteries always branch, so this is inevitable. You get the smooth, straight laminar flow. When you get to a branch, it has to like fork, and that causes turbulence. Turbulence, if you increase the turbulence, you increase the resistance to blood flow. Okay. I don't talk about that too much either. The one that's discussed most is the vasoconstriction, because that can be modified by the sympathetic nervous system. The last one, vasoconstriction. Now, vessel radius is symbolized by a lowercase r. Okay, so if you have a diameter of a blood vessel of anything, the radius is, half the diameter. So we kind of refer to that when we talk about if a blood vessel can constrict or dilate. If you have a blood vessel with a given radius, r, if you vasoconstrict due to sympathetic activity, S, Y, M, The epi, norepi. They can cause a vasoconstriction. Increase that sympathetic tone. You really decrease the radius. Okay. When you vasoconstrict, what you've done is you've decreased the radius, lowercase r, and you largely increase capital R. Okay, so what you have to understand is the relationship is a lot. So, do this. It's inversely proportional. If you affect the radius just a little bit, it affects the resistance to the fourth power. Okay. Now the arterioles are the resistance vessels, and that they help increase the BP the most. So vasoconstriction of arterioles really increases the BP. So here's a picture of that, and I kind of started to draw there. When you have sympathetic stimulation, you go from vasodilated to vasoconstricted. If you're vasodilated, usually what it is, the default is the parasympathetic is on. That should be on like most of your day. Except maybe when you're taking a test, right? You're stressed out, maybe the sympathetic turns on a little more, you get nervous. But when you're relaxed, that's on. You inhibit the sympathetic. Okay, so the default is parasympathetic on. The result is inhibit the sympathetic. Okay, the result of that is, I'll put VD, vasodilate. The result of that is reduce blood pressure as when you relax. Okay, so that's the thinking there for the left. When you vasodilate, you are increasing little r, you're decreasing big R. The more blood can flow out of the arteries, drops the blood pressure a little bit. That's kind of the effect there. So let's do the opposite of that. What if the parasympathetic is turned off? You remove the sympathetic block. Now you just fire epi, norepi, and the sympathetic fires, you're going to get vasoconstriction. When you vasoconstrict, you reduce the radius, increase capital R. That's the thinking there. And this is, say this is occurring at arterioles. If you're increasing the resistance to blood flow at the arterioles, you're keeping more blood in the arteries. Therefore, the result of vasoconstriction is to increase blood pressure. So again, to go back and review, here's how I'm trying to program your brain, right? You excite the SNS, that's the sympathetic nervous system. What's the effect on tunica medium blood pressure? So think of it in batches, okay? You turn on, okay, you excite the SMS. Which of these is occurring, 1 or 2?
Vasodilator.
1. If you turn on the sympathetic nervous system, you remove the sympathetic block, which is the same as you're exciting it. You vasoconstrict. That's the first thing. Sympathetic, you vasoconstrict. So I gave you the first one. If you vasoconstrict, what's the result? You increase the blood pressure. So just like, that has to like be like knowing your name. You kind of have to like know that. And once you get that rule down, a lot of things fall into place much easier for you. So you turn the parasympathetic on. What's the effect on blood pressure? Choose all that apply. Okay, well, if you turn parasympathetic on, which happens first? 1. If 1 happens, which happens as a result? 2. And if 2 happens, which happens as a result?
2.
Very good. 2 again. And that's kind of how you have to train your brain to think in the correct order of events happening in your body. Okay. And so to explain why constriction affects blood flow, if you consider blood flowing, and if you divide the flowing blood into shells in 3-dimensional space, the blood vessel would be considered layer 0 of flowing blood because it's not flowing at all. It's the vessel wall. But the actual flowing blood into layers, 1, 2, 3, all the way down to the center, the shell in the center has the fastest velocity of blood flow, hence the biggest vector arrow, right? As you get progressively closer to the vessel wall, there's more friction. So that's why you have the slowest velocity of blood flowing in layer 1. So the reason why if you modify the radius by vasoconstricting or dilating, the thinking is if you're constricted, you have more resistance because you have proportionally more shells in contact with the flowing blood and less in the middle for that free-flowing, fastest blood flow. So that with the more friction, you increase the resistance to blood flow, that tends to increase the blood pressure, and the opposite of out here. When you're more dilated, blood pressure drops, you have less resistance to blood flow because you have more of that laminar flow, more shells not in contact with the vessel wall, because that's the thinking there. Now if you did the math, and they've done the math for you, if you just reduce vasoconstrict from 5 to 4.2, that's only a 16% reduction in radius, but the flow is reduced by half. Okay, so. All right, that's a good place to stop. I'll pick it up here next time. What time are we starting Wednesday? Okay, I'll see you then.
No.